The torque of an electric machine occurs through the interaction between the flux linkage and the current. Usually, the flux linkage is kept as constant by the permanent magnet, or constant field current. Also, the electric machine can be modeled as a converter that converts the current to the torque or to the thrust force. The rotating speed of the electric machine is decided by the torque, friction, the load torque, and the inertia of the rotating part of the system under control. Hence, if the load torque, inertia, and friction are given, the speed can be regulated by the torque of the machine. So, to control the speed in the speed regulation loop of an electric machine drive system, the torque of the machine should be controlled, and the output of the speed regulator is naturally torque. In this video, the design of the speed regulation loop is discussed. We have already shown the subordinate current or torque control in detail in the last two videos. The design of a proportional and integral regulator, which is the most widely used regulator in the industry, will be described in a speed control system, where a mechanical system is driven by an electric machine, whose torque is controlled instantaneously. In the above figure, the torque due to the friction is considered as a part of load torque, and the current regulator is modeled as the first-order low-pass filter. In the case of a DC machine, it is assumed that the torque is directly proportional to the armature current, neglecting the armature reaction and other stray effects. We will use now the same servo motor driven with the same load condition, and with the current control system as in the last two videos. The current control loop can be assumed as the first-order low-pass filter, whose cut-off frequency is the bandwidth of the current control loop, decided in the last video. The sampling frequency has been doubled, and is twice the switching frequency. All control algorithms are executed within one sampling interval. The output of the regulator is updated at the next sampling point, after finishing the execution of the algorithm. The sampling point is peak and valley of the carrier wave. There are three distinct regions, where the slopes are -40, -20, and -40 dB per decade respectively. The first part from the left-hand side of the plot comes from the inertia of the mechanical load, and integral gain of the speed regulator. In this frequency region, the proportional gain can be neglected, compared to the integral gain. And the current regulation loop can be set as unity gain. The second part comes from the inertia of the mechanical load, and the proportional gain of the speed regulator. In this frequency region, the integral gain can be neglected, compared to the proportional gain. The second part starts from the region where the frequency is above omega pi. The last part comes from the current regulator and the load. In this frequency region, the speed regulator looks like only a proportional regulator, while the current regulation loop looks like only an integral term. This region starts when the operating frequency is over the bandwidth of the current regulation loop, omega cc. The speed regulator will be now implemented digitally in the discrete time domain, and the speed sampling is done at every 200 microseconds. To measure the speed or the position, the digital encoder is widely used, which generates pulse train, whose frequency is exactly proportional to the speed. The encoder can be classified as the incremental type, where the pulse corresponds to the relative position of the rotor, and the absolute type, where the pulse corresponds to the absolute position of the rotor. In particular, for the control of the DC machine or the induction machine, where the absolute position has no meaning for speed regulation, the incremental encoders are used without exception. The optical encoder consists of a light-emitting diode, a condensing lens, a rotating disc with slits, a light receiver that is usually a photosensitive semiconductor, such as a phototransistor, and microelectronics to process the output of the phototransistor.